All right. So here is our whole source file, right? We see that I have my imports again with the addition of tfds. I've disabled the progress bar. I'm loading MNIST, which is pretty straightforward. The first time you call this, it is going to download MNIST. I don't think MNIST is very large, although I forget the exact file size. I think it's in the area of 200 megabytes, although I don't remember for certain. Although thereafter, like, you'll have MNIST downloaded and it won't download it again, right? And then we have our toFloat function, which is the function we're going to be mapping, right? And it returns a tuple that contains this, right? Which first casts that image. So remember here that image is going to be a, I think it's 28 by 28 uint8 image, right? It's going to cast that to float 32, and then it's going to normalize it to be in the range 0 to 1, right? 255, right? Because that's the maximum range of one uint8 is 255, right? That's where that 255 normalization factor is coming from. And then this function is just the tf.onehot function, which is going to conveniently take a number and a number of categories and return a one-hot vector of type float32 that has that many categories with exactly this one, right, being 1 and the others being 0. And actually, just so we can inspect this, let us automatically comment all of this out and see what that is going to get us. So if we comment all of this out, right, we're just going to see test and train as it gives it to us natively, right? So we see that it is a data set, and the shapes of the things in the data set are 28 by 28 by 1, that's the images, and dimensionless. Why is it dimensionless? Because it's a scalar, right? 1D would be like an array, right? 2D would be like a matrix. 0D is just one thing, right? It has no extents. It's just one thing. So this is a sample, and then this is the number of the category label. We see that the types are uint8, unsigned integer 8 bits, right? So 1 byte, 1 unsigned byte, and that's the grayscale intensities, and an int64 that is being used to store the output index. Okay? Oops. So let's uncomment this stuff and see what that does. Okay? So again, it happened almost instantly, I believe, because these transformations are lazy. It's going to build up a representation of those operations, right? But it's not going to actually run any of them until we actually try to iterate over this data, like when we perform a fit, right? So now, if we look at what's in train, we see that we have added a batch dimension. Whoops. Our size is still 28, 28, 1. This size, though, is now 10. Why did it go from scalar, right, to size 10? Because that's the size the one-hot is, right? It's a one-hot of 10 classes, one for each digit, right, of which exactly one is going to be on at any given time. And they are both tf.float32, right? So they are a none by 28 by 28 by 1 dimensional array of floats and a none by 10 array of floats. And again, it's so why that leading none is coming from the fact that these are going to be batched. That's a batch dimension. Just don't worry about it right now, all right? I didn't want to cover this yet. It's not a complicated concept. I just don't want to get into it right now. I didn't want to cover this yet. But there's not really an easy way around it with these things. So we'll just sort of ignore it for the time being. All right. So, finally, and this stuff is just some fairly general model building code, right? You've seen all of this before, right? You've seen a lot of this last unit. So our input shape is 28 by 28 by 1 because it's a 28 by 28 sort of square grid of pixels of one channel. We immediately flatten it. We're going to push it through a 500 width dense layer, then 300, then 10. And we're going to use softmax and categorical cross entropy because that is our good final activation and loss for a classification problem. Okay? And we are going to use our test set for validation so we know how our model performs on unseen data. And if we push run, blink. This will take a minute. And I didn't even think about trying to do this and a stream transcode at the same time. Hopefully the stream doesn't go to hell. We shall see. Oh, I only had it do one epoch. That shouldn't be so bad then. But, because it's fun to just sort of throw maximum pain at my CPU, let's turn on the overliner. Right? So this is much larger than a lot of the networks we've done. Right? That's a lot of weights. 500 is. But realize how many weights are in the input, right? Or how many units are in the input, I guess I should say. 28 by 28 by 1, right? How many is that? $784. So part of my thinking with picking 500 is I don't want to try to narrow that too quickly, right? Every time you go from like a lot of units to a little bit of units, you're throwing away some information, right? And I don't want to try to throw away information that aggressively, right? We notice, though, so this is not, if there are a lot of units in this layer, this is not a particularly complicated or sophisticated layer, and after a single epoch of training, 1, right? We saw our validation loss go down to 0.1577, right? That's not super low. That's also not super high, given that it was only 1 epoch of training. Okay? And if we pick a slightly higher number, what the heck? Let's pick 5. So you'll get to we'll get to make some small talk while it crunches for 5 epochs. But what I anticipate us seeing is that our loss will become fairly small, right? So that is one of the downsides of this data set, right? It is actually fairly simple to get, or it is fairly possible to get arbitrarily pretty good loss with a sort of small, not very clever, not doing anything advanced network. All right. Couple more seconds, everybody. So yeah, there we go. Notice, again, right? So 0.1, not outstanding, right? We can do a lot better, but also not very high, right? Considering how not sophisticated this network is and how little training it's seen. And it seems to still be going down, right? And it's not fluctuating, right? If our network was going to perform poorly, we might expect to see the validation loss kind of going all over the place while our training set loss continuously improves. But we're also seeing the validation loss seem to keep going down, right? Here we go. Last one. All right. So, this is one of those times where I feel like I may have gone over this code way, way, way too quickly. I hope that's kind of going to be okay, because you can sort of just kind of cut and copy these couple of lines and they'll just work, right? But sort of one last little, reminder, right? Every part of this is important, right? We need to pick which of the splits we get. We want the test set and training set. I think this one only has these two, but other data sets have more. We don't want to have to pick which features we want. We know we're using this for supervised learning, so we give it as supervised true, and that will cause it to give us the input and label as like the two selected features, which makes it easy to just pass this thing straight into fit down here, right? This is a function that transforms one pair, right? One image label pair from the data set, and it casts it, right, to a float 32 and normalizes it and makes a one-hot vector. And then this is us applying that function to every element and then batching it, which we have to do because it's sort of designed to work that way. Okay. So a final little note here. There actually is something else slightly clever we can do. I wanted to produce a one-hot vector because that's how we talked about it, but we actually don't have to do that. So there is another loss, sparse categorical cross-entropy, and sparse categorical cross-entropy is designed to take just a number, right? So it is designed to take just the number of the category you want and not a one-hot vector. If we do that, we can drop this, right? This basically becomes a no operation. We just want to return the number we already had. So we can just do that. I think that should work. Yep. And that saves us not very much computation because making those one-hot vectors is not expensive, but it saves us just a little bit of typing and a little bit of work, okay? This is the same loss that cross-entropy was. It's just designed to take a number that is the number of the category instead of a one-hot vector. Mathematically, it's identical. Okay.